You know, every time you plug something into a wall, you're tapping into this huge, invisible engine that powers our entire modern world. And that engine, it runs on alternating current, or AC. Now, it might seem simple, but the story of how we figured out how to manage its complexity, well, it's absolutely brilliant. So let's dive in and see how it all really works.
So here's our roadmap. First, we're going to unpack the big challenge with AC. Then we'll get into the incredibly clever tool engineers invented to handle it, and we'll meet the key components you find in any AC circuit. After that, we'll see how they work together to create the magic of resonance, and finally, we'll uncover the genius of transformers, the tech that literally powers our world.
All right, first up, the AC challenge. What is it about the electricity in our homes that makes it so much trickier to work with than, say, the power from a simple battery?
Well, it really just comes down to this. Direct current, DC, is super simple. Think of it like water flowing through a pipe in one direction. It's constant, it's steady, it's predictable. But alternating current, AC, is way more like the ocean tide. The flow is constantly changing, rising to a peak, falling, and then completely reversing direction, back and forth, over and over again, in this really smooth, wave-like pattern.
And this right here really shows you the problem. Because of this wave, this sinusoidal pattern, the voltage and current are never the same from one moment to the next. You can't just use simple math anymore. It's like you're trying to do calculations on a moving target, which, believe me, usually means you have to break out some pretty heavy-duty calculus.
So how in the world did engineers solve this moving target problem? Well, they came up with this incredibly slick mathematical tool called a phasor. You can think of it as the secret language that suddenly makes AC understandable.
Okay, so what is a phasor? It's basically a snapshot in time. A really good way to picture it is to imagine a pencil spinning in a circle. That sine wave we saw, it's really just the shadow of that spinning pencil. A phasor freezes that pencil at one exact instant, and that snapshot tells you two critical things: the length of the pencil, which is the peak of the wave, and the angle it's pointing, which tells you exactly where you are in that cycle.
And this is where the magic happens. We take that tricky, always changing wave, we translate it into a simple static phasor, and poof, all that hard math just becomes easy. We can add them, subtract them, multiply them, all using basic algebra. Then, once we have our answer, we just convert it back to see what the actual sine wave is doing in the real world.
Seriously, without phasors, if you wanted to analyze an AC circuit, you'd be stuck solving these kinds of complicated differential equations.
But with this one simple tool, all of that chaos turns into simple algebra. It was an absolute game changer, pioneered by an engineer named Charles Proteus Steinmetz, and it completely revolutionized electrical engineering. It made everything so much more accessible.
Okay, so now that we've got our secret weapon, the phasor, let's meet the three main characters in any AC circuit: the resistor, the inductor, and the capacitor. And let me tell you, they each have a very unique personality when they're dealing with alternating current.
So in AC circuits, we have this bigger idea called impedance. It's the total opposition to the current. It includes the normal resistance we all know, but it also has this new thing called reactance. Think of it this way. If resistance is like constant friction, reactance is more like trying to run back and forth in a swimming pool. The faster you try to move, the higher the frequency, the more the water pushes back. It's an opposition that reacts to change.
And what's really cool is how each component acts differently. A resistor, well, it's the simple one. It just pushes back the same no matter the frequency, and the voltage and current waves are perfectly in sync. An inductor, though, which is basically a coil of wire, hates change. The faster you try to alternate the current, the more it fights back. This makes its voltage get 90 degrees ahead of the current. The effort has to come before the flow can catch up. And the capacitor, it's the exact opposite. High frequencies pass through it easily, but it fights back against low frequencies. This makes the flow rush in first, so its voltage ends up lagging 90 degrees behind the current.
So what happens when we put all three of these players, the resistor, inductor, and capacitor, together in one circuit? Well, we get something truly amazing, a phenomenon called resonance that is the foundation of pretty much all of our communication technology. Just look at this curve. As we sweep the frequency of the AC signal, something incredible happens at one very specific point. The inductor's tendency to push the voltage ahead is perfectly, and I mean perfectly, canceled out by the capacitor's tendency to pull it behind. They basically cancel each other out. And at that one resonant frequency, the circuit's total impedance just plummets, leaving only the simple resistance. And what happens then?
The current just rushes through at its maximum strength.
But that brings up a really important question. How sharp is that peak really? And, why should we even care about how sharp it is?
Well, the answer is something called the quality factor, or Q factor. If you have a high Q factor, it means that peak is super narrow and very, very selective. This is exactly how your radio works. A radio is just an LCR circuit with a really high Q factor. So when you tune it to 101.1 FM, it lets a massive current from that frequency flow through, while totally ignoring the stations at 101.9 and 101.3. Sharpness is selectivity. All right, let's tie this all together with the single most important application of AC, the one piece of technology that let it completely dominate DC in that famous War of the Currents. Let's talk about the transformer.
So, here's a real-world problem for you. Imagine you have to deliver 1 megawatt of power from a power plant to a town 10 kilometers away. How do you do it without having most of that energy just burn up as heat in the wires along the way?
The solution is the transformer. A step-up transformer has way more coils of wire on its second loop, which ramps up the voltage but lowers the current. A step-down transformer does the opposite. It lowers the voltage and increases the current. And this simple ability to change voltage is something that DC just can't do easily.
So what would happen if we tried to send that megawatt at the normal 220 volts you have in your house? It would be an absolute catastrophe. The current would have to be so enormous that nearly 99% of all that power would just be lost as heat from the wires. You'd be sending out a megawatt, and the town would get practically nothing.
But here's the absolute genius of AC. Before we send the power out, we use a step-up transformer to boost the voltage way, way up, in this case to 11,000 volts. And the result is a complete game changer. By sending the power at a super high voltage, the power loss becomes tiny. Now, over 99% of the energy actually makes it to its destination. Then, right before it gets to your house, a step-down transformer safely brings that voltage all the way back down to 220 volts for you to use.
So here's the key takeaway, because this is so important. The power you lose as heat isn't just proportional to the current, it's proportional to the current squared. So by jacking up the voltage by a factor of 50, we get to lower the current by a factor of 50. But that means the power lost to heat goes down by a factor of 50 squared. That's 2,500 times less waste. It's a massive exponential leap in efficiency, and it's all thanks to AC and the beautifully simple physics of the transformer.
So the next time you flip on a light, just take a second to remember that invisible engine humming away behind the scenes. This whole complex dance of sine waves, tamed by phasers, perfectly tuned by resonance, and delivered efficiently across entire continents thanks to transformers. Makes you wonder, right? What other hidden physics are powering your day?